Bridge and road construction combines advanced engineering, precision machinery, and skilled labor to create durable, efficient infrastructure connecting communities worldwide. Explosive demolition is a controlled method where specialists place precise charges to sever key supports, causing a building to collapse inward safely. At industrial sites like RMH at Teesworks, strict planning, dust and debris control, and exclusion zones protect workers and nearby neighbors during the efficient removal of hazardous structures. The BRC Brexter, used for flood protection works in Emmen, is a patented Swiss attachment designed for fast and efficient processing of concrete piles and pile walls. It operates up to 8 times faster and 60% cheaper than traditional methods, while ensuring higher safety and sustainability. Brexter exposes reinforcement bars within minutes, creating perfect pile-to-base connections without cracks. Moreover, 80% of the removed material is reusable gravel, reducing carbon dioxide emissions and promoting eco-friendly construction. Over the Easter weekend of 2018, Iron Rod Iran, in partnership with the construction company John Sisk & Son, successfully installed a new underbridge beneath the main Cork-Dublin railway line at Osberstown near Sallins for Kildare County Council. The work formed a key part of the Sallins Bypass project, aimed at improving local road connectivity and eliminating a potential traffic bottleneck caused by the existing level crossing. What made this project remarkable was the fact that the entire installation was completed within a single weekend, demonstrating outstanding coordination, engineering precision, and logistical planning. The underbridge itself had been meticulously constructed over several months prior to Easter. Instead of building it in place, engineers used an offline construction method, assembling the reinforced concrete bridge in sections beside the active railway. This approach offered several advantages. It minimized disruption to train services during the preparation phase, ensured greater safety for workers, and allowed for quality checks on each component before installation. Each precast section was carefully manufactured and stored near the track, ready for swift positioning during the short possession window. Work began precisely at 0:30 hours on Good Friday morning, immediately after the last scheduled train had passed. The railway track was first removed along with the ballast and subgrade layers to create sufficient space for the bridge installation. Then, using large cranes and specialized lifting equipment, teams maneuvered the massive concrete sections into place. Continuous collaboration between engineers, crane operators, and railway specialists ensured that every element was installed according to plan. The process required 24-hour operations under strict safety protocols and precise time management to meet the reopening deadline. Once all bridge sections were properly positioned and secured, crews immediately began reinstating the railway track. They replaced the ballast, compacted the formation, and relaid the rails with exact alignment to meet operational standards. Multiple safety inspections and track geometry tests followed to confirm stability and ride quality. By 10 o'clock on Easter Monday morning, the main track had been fully reinstated, and by 12:30 that same day, normal train services between Cork and Dublin resumed without delay. The successful completion of the Osberstown underbridge installation highlighted the efficiency and professionalism of both Iron Rod Iran and Sisk. It demonstrated how modern civil engineering methods, such as precast modular construction and advanced scheduling, can deliver complex infrastructure upgrades within extremely tight time frames. Beyond the technical achievement, the new underbridge brought lasting benefits to the region. It improved local road safety, reduced congestion, and supported the overall development of the Kildare transportation network. The replacement of the rail bridge at Cow Lane in Reading was carried out in two major phases: the off-site construction of the new bridge and the complex operation to relocate and install it in place of the old structure. The new bridge was built in a staging area adjacent to the railway, allowing work to progress without disrupting train services. Engineers assembled the steel framework on solid foundations, carefully aligning sections to ensure accuracy. Reinforcements and cross beams were added to create a robust structure capable of supporting heavy rail traffic. The deck was installed and secured, forming a complete bridge ready for installation. By preparing the entire structure in advance, the project minimized the time required on the active railway line and ensured efficient execution during the replacement phase. Once the new bridge was fully assembled, attention turned to the removal of the existing structure and installation of the replacement. First, heavy lifting equipment was brought into position, including self-propelled modular transporters. These specialized machines were maneuvered under the new bridge, raising it slightly off its supports. The massive structure was then carefully transported along a prepared route toward the railway corridor. Precision control was essential, as the bridge, weighing hundreds of tons, was moved slowly into alignment with its final position. Meanwhile, the old bridge was dismantled and lifted out, clearing the site for the new installation. After the existing structure was removed, the new bridge was rolled into place and carefully lowered onto prepared abutments. Engineers conducted precise adjustments to ensure a perfect fit and secure seating. Once in position, the bridge was locked down, and final connections were made to integrate it with the rail line. This coordinated effort allowed the replacement to be completed within a limited time frame, minimizing disruption to rail services and ensuring the new bridge was ready for operatio. The construction of the Olifants River Arch Bridge commenced with comprehensive geotechnical investigations, followed by foundation preparation on both banks of the Olifants River. Due to weathered rock formations, mass concrete blinding layers were poured, and high-capacity rock anchors were installed to enhance horizontal load resistance and foundation stability. Temporary structural steel trusses were then erected to support the self-weight of the in-situ concrete arch during construction. These trusses, weighing approximately 60 tons, were designed to slide laterally to support the symmetrical construction of the twin concrete arch ribs. The arch was cast in two halves using high-strength concrete, typically 50 megapascals, in custom-designed formwork. Precambering was applied to each arch segment to counter deflection and ensure the correct final geometry after removal of supports. Once both arch halves were complete, the support trusses were moved into their second position using 95-ton hydraulic jacks, aided by graphite grease to reduce friction. The arch thus acted as a compression element in the final structure. The bridge deck was then constructed using a twin-box spine design. It spans continuously across the arch without intermediate joints, reducing long-term maintenance. The reinforced concrete deck is designed to handle live loads from highway traffic, including heavy trucks, in accordance with SAN-RAL specifications. Its total length is approximately 125 meters, and the central span over the river is 90 meters. To reduce internal bending moments, concrete hinges were cast at the arch deck connections. These allow controlled rotation, improving durability and reducing stress concentrations. Reinforced piers transfer loads from the deck to the arch efficiently. Final works included installation of precast parapets, waterproofing, drainage, a downstream pedestrian walkway, and asphalt surfacing. The bridge now safely carries the N7 route, improving regional connectivity and demonstrating advanced South African bridge engineering. The construction of the Krhan Bridge, along with its connection tunnel and road, represents one of Turkey's most significant infrastructure projects, undertaken by Doğuş İnşaat. The bridge is located at the intersection of the Elazig-Malatya State Road and the Euphrates River, serving as a vital link between eastern Anatolia's 16 provinces. With a total length of 660 meters, the bridge features a 380-meter main span, a 180-meter rear foundation block, and a 100-meter approach viaduct. It is a cable-stayed structure supported by a 168.5-meter-high inverted Y-shaped pylon, ranking 4th in the world among single-pylon bridges of its class. A major milestone in construction was achieved on June 18, 2019, when the 6th steel deck segment was floated across the Euphrates and installed. Each orthotropic steel segment, part of the bridge's 25-section deck system, is fabricated in a specially equipped EN 1090-1 certified EXC4 workshop established on site. The 7th segment, weighing several hundred tons, was placed on custom-built pontoons using a 300-ton gantry crane, transported 2 kilometers by ferry, and lifted into position with a 350-ton heavy lift system. This innovative approach minimized environmental impact and optimized logistics. Once completed, the Krhan Bridge will stand as a key technological landmark, enhancing transportation efficiency between Malatya and Elazig while significantly reducing travel time and public costs. The project showcases Turkey's advanced engineering capabilities in designing and building large-scale, modern suspension and cable-stayed bridges. The asphalt paver is one of the most essential machines in modern road construction, designed to spread and level hot asphalt to create a smooth, durable surface. Before paving begins, operators must carefully complete a pre-paving checklist to ensure precision and safety. The screed must be heated evenly, paving width set according to the project plan, and the screed crown and slope extensions adjusted. The screed is then lowered into the correct starting position, and the end gates are set. The auger height is adjusted to be about 2 inches above the surface being paved, while the feed sensors are properly set. Before any hot mix is placed, a tack coat, an asphalt emulsion that bonds layers together, must be applied to a clean surface. As the emulsion breaks, the water evaporates, changing color from brown to black, indicating readiness for paving. When the asphalt truck arrives, the dumpman guides it safely into position and ensures the hopper remains between 1/3 and 2/3 full. The asphalt mix is transferred by conveyors to the augers, which spread it evenly in front of the screed. Maintaining a constant head of material in front of the screed is vital for uniform thickness. The screed then shapes the asphalt mat, controls the angle of attack, and establishes the correct paving depth. Following placement, a rolling pattern is used to compact the asphalt to the required density. The large steel wheel roller performs the initial compaction, followed by the pneumatic roller, which finishes the surface by adding final compression and smoothness. In commercial paving projects, many additional factors must be considered. The design of the parking lot is critical to performance and lifespan. The base layer is like the cake beneath the frosting of asphalt. If it is weak or poorly compacted, the asphalt will fail prematurely. Proper compaction, correct slope for drainage, and stable subgrade are essential. Since pavers move in straight lines, smaller or curved areas must be finished manually. Finally, engineers must select the right asphalt mix and thickness based on traffic load and local climate to ensure the pavement is strong, long-lasting, and visually appealing. The construction of a blind shaft begins with careful surface preparation to create a safe and stable working environment. The selected site is cleared of vegetation, debris, and unstable soil. A level working platform is established to accommodate cranes, compressors, ventilation ducts, and hoisting systems. The upper section of the shaft, known as the shaft collar, is then constructed using reinforced concrete. This collar provides structural integrity to the shaft mouth, prevents surface soil from collapsing, and serves as the foundation for lowering equipment. Around the collar, safety barriers, drainage channels, and access platforms are installed to ensure worker protection and environmental control. Following surface preparation, the sinking phase begins. The method of excavation depends largely on the geological conditions. In hard rock, the drilling and blasting technique is commonly used. Holes are drilled into the rock face at the bottom of the shaft, filled with controlled explosive charges, and detonated in carefully sequenced blasts. After each blast, the loosened rock, or muck, is collected using buckets, skips, or pneumatic hoisting systems and transported to the surface. Workers then clean and scale the walls to remove loose fragments before the next round of excavation. The process continues cyclically, drilling, blasting, mucking, and scaling until the desired depth is achieved. In softer or unstable ground where blasting is unsuitable, mechanical excavation techniques are applied. A shaft boring machine or road header cuts through the soil or rock with rotating heads, while conveyors or buckets transport the excavated material upwards. This method provides continuous operation and better control over wall stability, particularly in urban environments or near existing structures. During excavation, dewatering pumps are often installed to control groundwater inflow, maintaining a dry and safe working area. The use of ventilation fans is also essential to provide fresh air and remove dust and gases from the shaft. As the excavation progresses deeper, temporary supports are installed to maintain wall stability. The first layer typically consists of shotcrete, a high-pressure spray of concrete that adheres directly to the rock surface, sealing cracks and preventing small rock falls. In areas with significant stress or fractured rock, steel ribs or rock bolts are added for reinforcement. In water-bearing strata, waterproof membranes or cement grouting may be applied to prevent seepage. This stage is crucial to ensure the long-term integrity of the shaft and the safety of workers operating below ground. Once a certain depth is reached, engineers begin to construct the permanent lining. Depending on design requirements, the lining may consist of cast-in-place reinforced concrete, precast concrete segments, or a combination of both. The lining is installed in stages as the excavation advances downward. It provides not only structural strength but also a smooth and durable surface that resists water pressure and geological stress. The lining process involves precise placement, sealing of joints, and curing to achieve a watertight and stable finish. Once a certain depth is reached, engineers begin to construct the permanent lining. Depending on design requirements, the lining may consist of cast-in-place reinforced concrete, precast concrete segments, or a combination of both. The lining is installed in stages as the excavation advances downward. It provides not only structural strength but also a smooth and durable surface that resists water pressure and geological stress. The lining process involves precise placement, sealing of joints, and curing to achieve a watertight and stable finish. Throughout the entire process, safety and monitoring systems play a vital role. Workers operate in confined underground conditions, with potential hazards such as gas accumulation, water inflow, or falling debris. Continuous monitoring of air quality, wall movement, and water pressure is therefore essential. Communication systems, emergency hoists, and escape ladders are maintained to ensure quick response in case of incidents. Regular inspections and strict adherence to safety protocols are mandatory under all working conditions. Finally, once construction activities are complete, the site undergoes finishing and commissioning. The surface area around the shaft collar is restored, and permanent access facilities such as stairways, hoist towers, or ventilation structures are installed. The shaft is then integrated into the overall underground system, serving as a permanent ventilation route, drainage conduit, or service access. Ernst Concrete was responsible for pumping a 4,500 psi superplasticizer concrete mix for Lakeshore Engineering at the Riverbend Water Treatment Facility in Cherokee County, Georgia. The operation involved using high-performance concrete designed for strength, workability, and durability required in critical infrastructure. The superplasticizer additive improved flow without adding excess water, ensuring a dense and long-lasting structure. Pumping was carried out using specialized concrete pump trucks, allowing continuous delivery of the mix to hard-to-reach areas of the treatment plant's foundation and walls. Skilled operators carefully monitored pressure and consistency to maintain quality standards. This precise and efficient concrete placement contributed to the successful construction of key components of the water treatment facility, ensuring reliability and longevity for the region's water infrastructure. At the quarter-mile Edinburgh residential development, BAMTEC reinforcement was chosen as part of a modern and efficient concrete reinforcement solution. This project belongs to a series of over 100 successful installations across the British Isles, where BAMTEC technology has proven its reliability and efficiency in large-scale construction. The BAMTEC system is based on prefabricated mats, also known as reinforcement carpets, which are manufactured off-site under controlled conditions. Each mat consists of pre-welded steel bars rolled into a compact coil for easy transport. When delivered to the construction site, the mats are ready for direct installation, minimizing preparation work. The installation process is straightforward and efficient. Using a crane, the rolled mats are lifted onto the concrete deck. Once in position, the slings are removed, and the mats are simply rolled out across the designated area. This rapid deployment replaces the conventional method of individually placing and tying steel bars, which is often time-consuming and labor-intensive. The simplicity of the process ensures that large floor areas can be reinforced in a fraction of the time required by traditional techniques. One of the main advantages of BAMTEC is its ability to drastically reduce labor requirements and installation time. Because the reinforcement arrives in a ready-to-use form, fewer workers are needed on site, and installation can proceed without interruption. This leads to faster construction cycles and lower overall costs. In addition to speed, the system guarantees consistent quality. Each mat is produced using computer-controlled machinery and advanced planning software, which ensures accurate bar spacing, correct mat dimensions, and precise reinforcement positioning. This digital precision eliminates common site errors and ensures compliance with design specifications. Another major benefit of BAMTEC reinforcement is material efficiency. The optimization software used during the design stage calculates the exact steel requirements for each area, reducing excess material without compromising structural integrity. This intelligent use of resources results in significant material savings compared to traditional mesh reinforcement. Overall, the BAMTEC installation at Quarter-Mile Edinburgh demonstrates how modern prefabricated reinforcement technology can enhance productivity, quality, and sustainability in concrete construction. Through reduced labor, shorter installation times, improved precision, and material savings, BAMTEC provides a highly efficient alternative to conventional reinforcement methods, contributing to the success and innovation of contemporary building projects. The dismantling of the RoRo linkspan structure at Rosyth Ferry Terminal was part of a project undertaken for Forth Ports. The operation began with the demolition of a reinforced concrete HGV access ramp, which provided the foundation for the subsequent removal of the upper structural components. Once the ramp was demolished, the team proceeded with the careful dismantling, preparation and lifting of the associated upper ramp sections and their supporting elements. Heavy cranes were deployed to execute 3 major lifts during the operation. The first involved raising a 24-ton upper ramp section, followed by a tandem lift of the 85-ton main bridge span, requiring precise coordination between 2 cranes. Finally, the 62-ton portal support frame was lifted and removed safely. Each stage of the dismantling process was meticulously planned to ensure structural stability and site safety. The project demonstrated efficient teamwork and heavy lifting expertise, completing the complex removal of the RoRo linkspan with minimal disruption to operations at Rosyth Ferry Terminal.